When we draw the free body diagram for our rigid body and we choose our object of interest, we have to remove all of the supports that are attached to our object of interest, and then we need to model what those supports did to the object that we kept. When we were dealing with particles, this process was pretty easy. We typically had just ropes or cables or a normal force maybe acting on the object, and it was just some force, some concurrent force acting on the object. But there's a lot more options when we have a rigid body of what types of reactions are going to happen when we remove the supports. So just like for the particles, we remove the support, we're going to put in the reaction load that the support had on the object that we decided to keep. But here we're using the load a little bit more generally. A reaction load or a reaction can be a force and or a couple that support put upon the object that we still have. Now, we'll still have some things that remain the same like we saw with a particle. Ropes can only pull, cables can only pull, and they can only pull along their length, but we're also going to get more exotic types of supports as well. In general, what we want to think about when we're modeling what the support does to the object we kept is we want to see what type of support did it provide. Really what we want to think about is what motion was prevented because of the presence of that support. So in 2 dimensions, we need to think, did this support prevent translation along one axis? Did it prevent translation in the entire XY plane? Did this support prevent rotation around the Z axis? And any motion that it was prevented is going to be a force or a couple that support imparts on our object. So a direction of translation is going to be a force. A plane of translation we are going to model as 2 orthogonal forces. And if we prevent rotation around the Z-axis, it's going to be a couple. And this will expand when we get to 3 dimensions of thinking about translation in 3 dimensions and rotation in 3 dimensions. But for 2D rigid bodies, we can only translate in X and Y plane, and we can only have rotations around that Z axis. For a support, we want to consider in isolation of all other supports, what did just that support prevent the object from doing? How was it prevented from moving, rotating, because that one support was there? So we want to go support by support and individually think about what was prevented just from that support. So we'll go over some common supports and how we are going to model them. But most importantly, in 2D or 3D, if we just think, what does this support prevent from happening, we're going to be able to model it correctly. And then include those forces and that moment, if necessary, in the free body diagram. So again, for any support that we are going to be encountering, if that supports translation on just one axis, we are going to put a force along the direction of that axis. If in 2 dimensions all translations are prevented, then we are going to model that as 2 orthogonal forces. We can also still have normal forces. The same rule is going to apply as it did for particles, that a normal force is always going to act perpendicular to the surface of contact. And a normal force can only push on the object of interest. If we have a rope or a cable, those can only pull on our object of interest and only along the direction of the cable or the rope itself. And for all other types of connections, I'm going to suggest again that if we don't necessarily know if it's a push or a pull, if the object would be in tension or compression, I'm going to recommend always assuming tension and letting the math tell us if we're right or wrong. Now with rigid bodies, we have to think about also the rotation, but only around the Z-axis, since that's the only axis we can rotate around if we are able to treat something as 2-dimensional. So for a support, if the object cannot rotate because that support is there, we are going to model that with a reaction couple or a reaction moment at the point where the support is connected to our object of interest. Now, typically, rotation clockwise or counterclockwise would be prevented by a support. So if we don't necessarily know upfront which direction is going to be countered, then we can just assume it's going to be positive and draw it as a counterclockwise moment. And once again, once we go through the math, we're going to see if the reaction moment that we put down is positive or negative, and that will tell us if our assumption was correct or not. There's only so many combinations of translations or rotations that can be prevented in 2 dimensions. So here's some common ones that we're going to encounter. So first, we have a cable connection, and it's going to be modeled just like we had it for particle equilibrium, where it's a force in the direction of the cable that is going to be assumed in tension. We can have a link, which we also saw these when we were dealing with particles. Now the link can carry tension or compression. Just like with particles, I'm going to recommend that we always assume that the link is in tension. And we know that for a link, that the force is going to be in the direction of the axis of that link or of that bar. We could assume compression like we have in the second picture, but again, for consistency, I like always assuming that we are in tension. We're going to sometimes see a roller, and we're going to be making the assumption that a roller is going to be frictionless, in that there'll be no force along the axis that the roller can move. So again, we want to be thinking about what motion is allowed, what motion is prevented because of a support. So like in the case of a roller, it can freely move along the axis that the roller can roll. So along the slope of this, there's no motion being prevented, so there will be no force in our free body diagram. However, because the roller is in contact with this floor or the ground here, it's not able to move perpendicular to the surface. And if we see how it's modeled over here, we're going to say there's a force perpendicular to the surface because that's the direction we cannot move because of the support. However, there's no force parallel to the surface because we are saying that the roller is allowing free movement along that axis. And with more supports, we can have a roller that is confined inside a slot, in contrast to the normal force we had before where the roller was just in contact with the surface. Really, it just can't move into the surface. The surface is not preventing it from moving out from the surface. In a case like this, both directions of movement are going to be prevented, so it could be a force up and to the right or down and to the left, since the roller can't move in either direction along that axis. We can have a rocker, where this is modeled really the same as a roller, where the rocker in contact with the surface prevents it from moving perpendicular to the surface itself. It can't just fall through the surface. Now this again is a case where the surface really is only preventing it from moving down and to the left in this picture, but the surface doesn't grab it if it were to move up and to the right. So in the modeling here, we are specifically modeling it as the surface pushing on the rocker. The surface is not able to pull on the rocker. In the static equilibrium problems we're going to be doing, rarely will there be a case where we would need or want the surface to be able to grip on the rocker and prevent it from moving it up to the right. But in reality, that could be the case, and some of our assumptions could be wrong. So for example, here, if we model it pushing on the object, and we find that our F value were negative, this can't be the case, because that would mean that the surface would be grabbing the rocker and pulling it rather than pushing it up and to the right. So that can be an indication that we either modeled it incorrectly, we made a math mistake, or possibly for this to be in equilibrium, it would require the surface to grab onto the rocker and hold it down, which would be physically impossible. We can have a smooth surface, which is going to be basically just like a roller because we are assuming that there is no friction, so there's going to be no force, there's going to be no impedance of motion parallel to the surface. However, once again, like the rocker, like the roller, the surface is not allowing movement perpendicular to its surface. We can see here a collar connection with a pin. So now we're going to also have to think about the rotation that's being prevented. In all of the cases 1 through 6 and 7 that are mentioned here, there's nothing preventing rotation of our object. So for example, on the smooth contacting surface, we can translate the object along the surface, parallel to the surface. We cannot translate it freely perpendicular to the surface. And if we think about rotation at this point, there's nothing that stops it from rotating around that z-axis, the axis that is coming out from the picture to us. Same is true with the rocker, the roller, or the pin, and everything else. A rotation at that point is not being prevented. The same is true here with this collar. It's allowed to slide along the axis of the pipe that the collar is on. However, it cannot move perpendicular to that surface. So there is a force that prevents it from moving along this normal axis to the pipe. But because of this pin connection, there's nothing that's stopping us from rotating our object around this point. And when we're thinking about, does it allow it to translate? Does it allow it to rotate? We want to think about it in terms of small translations, small rotations. Certainly, if we try to rotate this too much, or we try to translate it too much, it's going to bang into the top wall or the bottom wall there. But we're thinking about very small translations. Are they going to be prevented? No. Small rotations, are they going to be prevented? No. And finally, the last set of pretty common types of supports that we're going to see in 2 dimensions is going to be our object pinned to or hinged to a surface. So if we think about here, how this object can move, we can't move it left or right because the pin is preventing this point from moving to the left or the right. We can't move it up or down because the pin is there. And actually in any direction in the XY plane, all translation is prevented. So what's actually happening is that the pin is going to be exerting some force in some direction on the object that we kept. However, mathematically, instead of having a force at some angle, it's going to be easier for us to model it as 2 components of that force, a horizontal component and a vertical component that are going to be parallel to our coordinate system. However, the pin, again, at least for small rotations, we can take our object and we can rotate it around that z-axis, and the pin is not going to prevent that from happening. And if we look at a fixed collar, we look at our member, it is able to translate along the axis of the pipe that the collar is wrapped around, so no motion is prevented along the axis of that pipe. However, we cannot translate it normal to that axis. Because we cannot translate it normal to the axis, there is a force normal to that axis. And think about rotation around the z-axis. If we tried to take this and rotate it around the z-axis, the collar, because it's connected to the pipe or it's wrapped around the pipe, is not going to allow us to freely rotate this around the z-axis. So in our model here, we are modeling that prevention of rotation as a moment or as a couple. We don't know its direction because this can't rotate clockwise nor counterclockwise. So we can just assume for our picture and then for our equilibrium equations that the moment that the collar is going to exert on the member that we kept is positive counterclockwise. And finally, we can have a fixed support, or sometimes called a built-in support. So here our object is embedded into a wall or into the ground. So again, if we try and move this object left-right, we can't because it's stuck inside this surface. If we try and move it up or down, we can't. It's stuck inside the surface. And in fact, anywhere in the XY plane, translation is prevented. So like the pin, because all translation in the plane is prevented, it really is going to be exerting a force in some direction on the member that we kept. However, once again, for the sake of making the math easier, we can just decompose this right away into an x component and a y component of that force. Now, unlike the pin where we could rotate around that z-axis, this fixed connection is preventing that rotation as well. We cannot rotate it even a little bit around the z-axis. So because rotation is prevented, we're going to model that as a moment acting on the object that we kept. So in a fixed support, we see that we have all 3 reactions happening there. We have 2 components of force, and we have a moment or a couple acting because all motion, translation, and rotation are being prevented at a fixed support.